Hi, welcome to Math 150, Section 2, 2021, Lecture 17. And it is now displaying the screen in a different size than it did in the first session, even though it's at the same location. So what we're going to do today is going to do more examples of integration. The hardest part of these problems is figuring out what are the bounds of integration. You often have a choice over what coordinate system to use. For some of the problems, even if I wished to be evil and try to confuse you, I can't hide what to use. Give me an example of a problem where it's clear what coordinate system you should use. If you're integrating over a circle, and you should probably use. Okay, what else? If you're integrating over a rectangle, you probably use rectangular, try to use the coordinates, but similarly, you probably want to use cylindrical and sphere is going to be a sphere. It doesn't mean that it has to be, but it just means that, almost surely that would be an excellent choice is to try to do this in spherical. There are often more than one ways to do some of these problems. And so if one of your approaches is not working, try something else. I am going to do different, some of the examples are going to be different than the ones in section 1. So if you want to see more examples, just go to the section 1 video. And you can just, of course, fast forward and skip ahead to get to something that might be slightly different. One of the problems we did there was from the homework, the integral was 1 over 1 plus x squared plus y squared. And we were integrating this over a quarter circle. Now, when you see this, you should be thinking polar coordinates. And when you switch to polar, the dx dy, this is going to become the theta over 1 plus r squared. And because the derivative of 1 plus r squared is 2r, I can multiply by a 2 and a 1/2. And this is ideally suited now to do the integration. Okay? You could try to do this directly. And so just to show you the algebra games you can play, I could write this as 1 over 1 plus y squared plus x squared. And let's do the integration with respect to x first. I could pull out a 1 over 1 plus y squared. I have 1 over 1 plus x squared over 1 plus y squared. I could let u equal x divided by the square root of 1 plus y squared. So then u squared would be x squared over 1 plus y squared. Du would be dx over the square root of 1 plus y squared. And because y is a constant, this would shift this to a mess in y times 1 over 1 plus u squared. Have we seen a function whose derivative is 1 over 1 plus u squared? We saw that last month. That was arctangent. So if you happen to remember the derivative of arctangent is 1 over 1 plus u squared, we've got that over here. Of course, then we'd be left with this nightmare in y that we would have to do. But this is one way to possibly approach it. Much better is to just directly shift and to do this in polar coordinates. But depending on how you do algebra, there's often more than one way to do a lot of these problems. At the end of class today, if there's time, I will go through how to integrate cosine squared over a nice interval. One way is to find the antiderivative for cosine squared, which can be done, but you have to do some trig games. Or the other way is to do some symmetry. Okay. So again, there's frequently more than one way to do these problems, but some ways are going to be better than others in terms of having algebra simplified. So one of the questions somebody wanted to do was one of the homework problems. So this was number 42. And so for this one, we are told we have the intersection of two paralleloids. And so the first is z is x squared plus 2y squared. And the other one is z is, I think, 12 minus 2x squared minus y squared. And so we want to figure out what is the volume between them. So it's going to look something like this. And of course, you should imagine that this is being spun. But what's nice is because they're paraboloids, hopefully things aren't going to be too bad. So let's try to figure out what the intersection is going to be. The intersection is going to be this nice region over here. And so we'll have some region over here. We go up and we hit the top paraboloid. We go down, we hit the bottom paraboloid, and their difference is going to then be the height. And if we integrate that height over this region down here, that will give us the volume. So really what we're doing is we have an x integration, a y integration, and a z integration of 1, dz, dy, dx. That gives us the volume. But that's as just integrating over x and y, z top minus z bottom. Okay. So let's first figure out how do we find the region of intersection of these two paraboloids. How do we find the points that are on both of them? What do we do? So how would we find the points that are on both the upper paraboloid and the bottom paraboloid? Set of equal to 0. So intersection, we would get x squared plus 2y squared is equal to 12 minus 2x squared minus 2y squared. Let's put all the x's on one side and all the constants, all the x's and y's on one side, all the constants on the other. So when we bring this over, we get 3x squared plus 3y squared equals 12. It is screaming, please divide by, yes? No. This is a typo over here. It should be 2x squared minus y squared. So I agree that it should have been 4y squared if we use the numbers I wrote on the board, but given that my hand is just working independently of my mind right now, I know what's happening. And so this is set up to give us a really nice shape. What happens when we divide by 3? We get it's the same as x squared plus y squared equals another radius 2 squared. So this is a circle of radius 2. So it's set up to give us a nice plot. And so now we want to integrate over the circle of radius 2. And now what's z top going to be? Which one is the top, which one is the bottom? Do you think the x squared plus 2y squared is the top, or do you think it's the 12 minus x minus 2x squared minus y squared? Yeah, because if you think about this, this is going to start off high, and as x and y get larger, moving away from 0, 0, it's going to be coming down. And this one, when x and y is 0, it starts off on the bottom at 0, and as x and y increases, it comes down. And so I'm going to get the difference between the two. So it's going to be 12 minus 2x squared minus y squared minus x squared plus 2y squared. So it's the integral over our circle. So we're going to have 12 minus 2x squared minus x squared is minus 3x squared. Minus y squared minus 2y squared is minus 3y squared. And now we have to decide, do we want to do this integral in Cartesian, or do we want to do this integral in polar? When you see an integral over a circle, what is your default go-to? Polar. And in fact, this is particularly nice because this is the same, I can pull out a 3, it's 3 times the integral a circle of 4 minus x squared plus y squared. The integrand depends only on x squared plus y squared. There's no theta dependence. So when we're doing these problems, there's many ways of doing it. It's really nice when you don't have the theta dependence. It's really nice when your region is a rectangle and the bounds of integration don't depend on each other. So it doesn't matter what r is, theta is always going to go from 0 to 2 pi. It doesn't matter what theta is, r goes from 0 to 2. Yes? I'm sorry, what happened to the... Are you talking about this line right here? This line? Oh, the intersection over here? I'm sorry, so what is the question about this circle? Yep. It's just hard to hear when you're far away with the maps. What do you mean by reduce? That's always what the circle is. The circle is just not in the xy plane, it's a little bit above. Technically, this circle is at a certain height. The intersection is not going through the origin 0, 0, 0. So the circle is actually lifted a little bit in space. It's floating above the xy plane. It's higher than 0, it's lower than 12. And if we wanted to, we could figure out exactly where that circle is located. But to some extent, it doesn't really matter. I can just adjust my polar coordinates to live on that circle. The height of that circle is immaterial. What matters is that each point in the circle, I go up to z top, and I go down to z bottom. And so I have this height value for each point in the circle. And so if we want to do this in Cartesian coordinates, we could do that. And then, x would go from -2 to 2, and y would go from minus the square root of 4 minus x squared to the square root of 4 minus x squared. In polar, it's much easier. So we need f of xy is converted to f of r cosine theta, r sine theta. Normally, what you would have to do is you would take your integrand, 4 minus x squared plus y squared, and replace x with r cosine theta, and then you would replace y with r sine theta. But because we do this so many times, we know r squared is x squared plus y squared. So whenever I need to do anything in polar coordinates, if I ever see x squared plus y squared, I don't have to write r squared cosine squared theta plus r squared sine squared theta. I can just directly go to say it's just r squared. And so my integrand is just going to be 4 minus r squared. And then I have to figure out what is the region of integration. And so here, I integrate theta goes, r goes. My function is 4 minus r squared, and I have to figure out what comes in here. So what is my theta bounds for integrating over a circle of radius 2? So what would theta go from? 0 to pi. And what would r go from for a circle of radius 2? So r would go from 0 to 2. And now we're using the fact that we're integrating over a circle of radius 2. We just don't care where the height of that circle is. And then we have to remember the exchange rate. In polar coordinates, dx dy goes to r dr d theta, or if you want dr r d theta. And if you think about what's going on, if x and y are in meters, then the area is in meters squared. dr d theta is only in meters. The angle has no length. But r times the angle does. You know, r d theta does have a length. It's not bad to view it as dr times r d theta, but when you actually want to do the integration, it's better to have all the r's together. And so it should be r dr d theta. It's very nice when you have an integral over a rectangle and the integrand only depends on a product of the two variables, on a function that's a product of r and a function that's a product of theta. They don't mingle. Because then you can split it into two separate integrals.
Can you explain why dx dy is r dr?
Sure, I will do that after this.
Oh, okay.
That's fine. That was in the video, but I'm happy to do that after.
Yeah, I saw the video, but I...
Yep, I will explain that. I will explain that. It's the conversion factor. That's where the meat of multivariable calculus is the conversion from r dr d theta to dx dy or vice versa. And this is an example of the change of variable formula. I will be careful because this is being recorded. My freshman year, we had a little bit of time at the end of a wonderful combined year-long class of multivariable calculus, linear algebra, vector analysis, and point set topology. We moved at a great pace. And we proved the change of variable formula in an incredible degree of generality. I truly believe we used every letter of the English alphabet and a good amount of the Greek. And you can prove these theorems in tremendous generality. We are focusing on this course, for the most part, on some very special cases. Cylindrical, spherical, polar. These are the ones that frequently arise in practice, but if you're going to go further, it's nice to know that you can have these exchanges. So we can write this as a product of the theta integrals. We'll have 3 integral theta goes from 0 to 2 pi. What's the function of theta? If I want to write this as a function of r times the function of theta, what's the function of theta? What's the function of theta? I'm sorry? D theta, or actually, if you want, 1 d theta. It's the simplest possible function you can have. It's just 1. Well, maybe I could give you the function 0, but then I wouldn't really be spending much time doing the integration. And then what's the function of r? Which is 4 minus r squared times r dr.
And you can just separate it out like that?
I'm sorry?
And you can just separate it out like that?
Well, the whole point is, if I integrate with respect to r, there's no theta dependence. I can just do the r integration first, and the r integral is just going to be a number. And now, because that's a number, I can then just do the theta integral. Here is my number. Because it's a number, I've just moved it to the right of the d theta. It's a number. You can only do this because the integrand splits as a product of r and a product of theta. So whenever you have things that split over a rectangular region, you can do this. If the bounds of integration depended on theta, different story. So what would the theta integral be? Well, I need a function whose derivative is 1. Can somebody give me a function of theta whose derivative is 1? Theta. So it would just be theta evaluated 0 and 2 pi. And now for this one, r equals 0 to 2. How should I rewrite 4 minus r squared times r? Yes. So which Newman transcendentalist should be on? So before we do the integration, let's look at it. It's just 4r minus r cubed dr. And the advantage of this is now this is a product. Now, what function has derivative 4 minus r squared times r? I don't know. But now this is 2 easier functions to work with. So the first one is going to be 3 times 2 pi. And now I need to find the antiderivative of 4r minus r cubed. Well, the function that has derivative 4r would be 4r squared over 2. And the other one would be r to the 4th over 4. and we evaluate this at 0 and 2, we get 6 pi. When we put in 2, we get 16 halves minus 16 fourths. So it should just be 16 fourths, which is also known as 4. So it should just be 24 pi. Okay. Hopefully that's the same as we got in the book. Good. So the question is this answer reasonable? So whenever you have a problem, it is always good to ask, is this answer reasonable? Well, I'm going to kill this part over here. And we're integrating over a circle of radius 2. What is the maximum possible height you could have when you look at the difference between the two parabolas? So the max height is 12, and what's the minimum height? 0, because the two parabolas intersect along here. And so what's the area of here? The area of a circle of radius 2 is 4 pi. So we know 0 times 4 pi is less than equal to the integral is less than equal to 12 times 4 pi. So 0 less than equal to the integral less than equal to 2 times 24 pi, right? And our answer is exactly halfway in between. It is the coincidence or something really interesting is going on, that the answer is exactly halfway in between. But it tells you that our answer is at least reasonable. It is smaller than the maximum, wider than the minimum. It involves a pi, and we have circles going on, so I'm not surprised that a pi is playing some role. Okay, any questions on this? Okay, so the question that was asked is, why does dx dy become r dr d theta? So the change of variable formula is the key tool in understanding a lot of this. And it's typically not covered in great detail in the first course, but in some of the special cases, we can explain where it's coming from. And so let's imagine we have a circle. Here's an angle theta. Here's a radius r. Not drawn to scale. Here's a delta theta. Here's a delta r. And so we have some kind of infinitesimal element like this. Okay? And so we're basically trying to chop up the circle. If this length is r, what is the circle radius r? 2 pi r. And so if I have an angle delta theta, what's the length of that arc? I'm just blowing things up. Delta r, this angle is delta theta. What would that length be? The whole circle has 2 pi for its angular measurement, and I multiply by r. So if I only have delta theta, the fraction of the circle I have is delta theta over 2 pi. That's the fraction of the circle I have. And the perimeter of the whole circle is 2 pi r. So this is going to just be a length, r delta theta. What would the length of this section over here be? This would just be r plus delta r times delta theta. if you are Bill Gates or Jeff Bezos, do you care about $1,000? It is a low order of magnitude. What about $1 million? Maybe $1 million is enough that you care a little bit about, but not a huge amount. So if you want, think of the delta theta and the delta r's as on the order of, 1/10,000th of the net worth of your truly mega rich. The delta r delta theta would be, say, 1/10,000 squared. And if you had a delta r delta theta delta r again, or delta r delta theta, if you had 3 of them, it would be such a low order of magnitude. Each time you go down, the effect is less important. I mean, the limit as you get smaller and smaller and smaller, it's not going to matter. If I approximate this as a rectangle, the area is approximately, r delta theta times delta r. Right? I want to just approximate the area of this and say that this is approximately a rectangle. The fact that things change a little bit, it's going to give me a low order term, plus a correction involving delta r squared delta theta. And this is going to be so much smaller that when we do our Riemann sums, the delta theta delta r is going to go to like a dr d theta. And this would have an extra dr. This would have something that's so small it goes to 0 in the limit. Another way, a better way to look at this is what's the area of the big circle? Big circle is pi r plus delta r squared, right? What's the area of the small circle? And of course, the small circle is almost the same size. It's pi r squared. What fraction do we have for this segment? Delta theta over 2 pi, right? If delta theta was 2 pi, we'd have the whole thing. So to figure out, I'm just trying to look at this small section over here. It's just going to be the area of the big circle minus the area of the small circle. That would give me the whole ring on the outside, but I don't want the whole ring. I just want delta theta over 2 pi of it. So when I expand this out, I have pi r squared plus 2 pi r delta r plus pi delta r squared minus pi r squared times delta theta over 2 pi. Well, now if you look, the pi r squareds cancel. We have 2 pi r delta r times delta theta over 2 pi. The 2 pi's cancel, and that's going to give us an r delta r delta theta. And the next term, we're going to have pi, 2 pi will have a 1/2 delta r squared delta theta. This correction is so much smaller than that. It has an extra delta r. It's going to be insignificant in the limit. So approximating this as a rectangle, gave the main term and the average term of size this. I can actually calculate the average term exactly in this special case. Yes.
So do you just ignore it?
So in the limit, it doesn't contribute. If you think and go back towards the Riemann sums, when we have our sum, delta r would be maybe like a 1/n, maybe delta theta would be 1/n. We're chopping them up into n pieces.
What, is the limit of what then?
Just breaking the circle up into all these small little segments.
So it's r goes to what?
So maybe we'll have,
Oh, it's r and delta r, or r minus delta r goes to
So let's say the circle had a radius of big R, and we chop it up into n pieces. So it's big R divided by n. And then delta theta would be 2 pi over it. We divide the n goes into n pieces. And that's going to give me a lot of small little grids. If I looked at this in my polar coordinates, here's my R, here's my theta, here's 2 pi, here's capital R. I'm chopping it up like that. And so for each one of these pieces, I then evaluate the function. I find my upper bound, my lower bound, and I just have to say, what area does each one of these blocks correspond to? And the area is not just length times width. I have to remember this kind of weighting factor. Because really what I'm doing is I'm chopping my circle up. My circle is being chopped up like this. And I'm just finding the area of each one of these boxes and multiplying by the value of the function. And because I have an extra delta R, and the limit as things get very, very small, I'm going to have a sum. K goes from 1 to n to the R. I'll have maybe a sum. L goes from 1 to n to the theta. And even though delta R and delta theta are small, because I have n squared terms, n squared times 1 over n squared is going to be a reasonably sized number. But over here, I'll have n squared times 1 over n cubed. And so because this has an extra delta R, it's not going to contribute in the limit. So when you go through and you look at the Riemann sums, the extra delta R is such that the contribution is insignificant in the limit. So just when you go through and start doing all the calculations, let's say the function f of x, y is just identically 1. I'm just trying to calculate here. I would then have 1 times from this piece, it would be r. And so r would be k r over n. And my theta would be 2 pi over n. And then I would just have an extra delta R from the other. So this should be, this would be my R. My R over here. My delta R would then be R over n. And then my theta would be 2 pi over n. That would be the first term. Here is the R, here's the delta R, here's the delta theta. The next piece would be plus 1/2 delta R squared. So it would be R squared over n squared, and then 2 pi over n. Yes?
Where does that L come in?
Well, I have my sum over my theta and my sum over my R. So I have my R pieces. I have, when we did, for the x's, we did 0 over n, 1 over n, 2 over n, 3 over n. So here the k is going to be giving me my R pieces. 0 times R over n, 1 times R over n, 2 times R over n, 3 times R over n. The L is going to be giving me my stuff, my thetas. 2 pi, 0 times 2 pi over n, 1 times 2 pi over n, 2 times 2 pi over n. I'm just counting them all up. When you look at this piece, I have an n cubed, yes?
Sorry. So, like, I get that it gets really small, but, like, how does it disappear altogether?
Well, because you have an n squared in the sum, you have n squared terms. You have 1/2 capital R squared 2 pi, that's a fixed constant, and you divide it by n cubed. So this piece is going to give you, the second piece, it's going to give you pi R squared n squared over n cubed. That's pi R squared over n. That goes to zeros and goes to infinity. As you take finer and finer pieces, the contribution from this is going to get smaller and smaller and smaller, and it's going to tend to 0. And that's why we can ignore it, because it has an extra factor of delta R. You might think that this piece is in danger because you have 3 n's. You have an n cubed, we only have an n squared, but we have k. And k is ranging from 0 to n. So the average value of k over n is 1/2. So you really lost one of the ends over there. You really have just an n squared that's canceling with the n squared over here. So the first piece is actually going to be okay. And if you go through, you will actually get pi r squared. If you take the average value of k as 1/2, that 1/2 times 2 pi is going to give you pi capital R squared. Here's the area of the circle. So the whole point of this is there is a way to justify why dx dy becomes r dr theta. We have to look at, when we put things into polar coordinates, what is the area of that infinitesimal segment? And it's not delta r times delta theta. It's r delta theta that you need for the length over there. And that's why it becomes r dr theta. This is one of the more technical parts of the course, where this stuff comes from. It's not bad to have an idea of why this stuff is true. But the main thing to think about is when we chop things up, we have really small contributions, but we have a whole lot of them. Do you ever see the demotivation posters? Like you see the Titanic sinking, and if there's mistakes, maybe the purpose of your life is to serve as a warning to others. I put this on my. One of them is it's a picture of the ocean, and it's no drop ever thinks it's the problem. So each little thing is insignificant, but if you have a tremendous number of them, it can become significant. So when we chop things up in one dimension, what do we do in one dimension? We chop things up. Here's 0, k over n, k plus 1 over n, n over n. We chop them up, and we looked at, here's my function, and we found the lower bound, and we got the box like that, and we found the upper bound, and we got the box like that. And we found a underestimate to the area of the curve and an overestimate where they were sandwiched in between, they converged to a common value. The length here is really small, it's 1 over n. When n is huge, it's insignificant. The area of any one box is so small you can throw it away. It's not really noticeable. But we have n of them. So each one of them is small, but of size 1 over n. If I have n of them, it's going to contribute of size 1. So a bunch of small contributions can contribute. When we were looking at proving things, we ended up using the mean value theorem to show that we had another error term that had an extra n in the denominator. And we had our bound for f prime, and when we looked at f of uk minus f of lk, this was f prime at some point times uk minus lk. And if we take absolute values, this was us equal to the bound for our derivative, and then uk minus lk, that gave us an extra 1 over n. Because the distance between the left and the right endpoints between the uk and the lk is at most 1 over n. And so what this is telling us is that the difference between f of uk and f of lk is something of size 1 over n. And when you multiply that then by the length, you get a 1 over n squared. So even if you sum it n times, you only have n terms where each term is of size 1 over n squared. N times 1 over n squared is going to be of size 1 over n. And so it's not going to be significant. So the same thing is true over here in this problem. We just have an extra 1 over n because we now have 3 infinitesimals. In one dimension, we should only have 1 infinitesimal, a delta x. In 2, we should only have 2, say delta r, delta theta. Because we have 3 of them, the third one is going to be enough to just push us into the realm where it just doesn't contribute. Does this explain things? So in the limit, we don't really have to worry about the delta r squared delta theta. You can see it has an extra delta r relative to all of these. So if delta r is 1 over a billion, then that means this piece is going to be 1 billionth of that. Then make delta r even smaller, so it's 1 over a quadrillion. And it'll be 1 over a quadrillion of that. Then make it 1 over a googolplex. And so you can keep doing that and making it smaller and smaller and smaller. Okay, so The difficulty is in proving what these change of variables are. And so the easiest case to do is the polar case, which we just did here. Or maybe cylindrical now, because cylindrical is basically just polar, where you're just dropping things. You're sweeping out circles as you fall. Spherical is a bit harder. And so for a sphere, I'll have something like this. I have to figure out what is the range from rho to theta and to phi. And so phi in our class is the angle coming down from the z-axis. In physics, we often have that as theta. So you just have to be very careful when you look at different books. So rho is going to go from 0 to the radius of the sphere. Theta is my xy variable. Theta just goes from 0 to 2 pi. And phi goes from 0 to pi. We have to figure out how does dx, dy, dz transform. It should be something d theta, d phi. Now, what units will dx, dy, dz have? So what would be the units of dx, dy, dz? Meters cubed. What's the units of d rho, d theta, d phi? Meters. So you can immediately tell me part of the change of variables. What has to come here? Meter squared. How can I get that? It has to be a rho squared. And you should really view it as a rho d theta, rho d phi to get those. Now the more interesting part is you have a sine of phi as well. So you have to remember it's sine of phi. The nice thing is it shouldn't be theta, because theta goes from 0 to 2 pi. If I try to sine of theta, I would actually get something that was negative at times. If I try to cosine, I would also get something that's negative. Of these, the only quantity that's going to be positive on the whole band is the sine of phi. To see why that's the right thing to look at, if I go back to this picture, if I have a radius rho over here, then my z-coordinate is just going to be rho cosine phi, and then this length over here is rho sine phi. So I'm now doing polar coordinates with r equals rho sine phi. And we know that polar coordinates, the dx dy, should go to r dr d theta. So that should make it seem plausible that it should be, rho sine phi d rho d phi, or d. This is not a rigorous proof here. I'm just trying to motivate why we should be having a rho sine of phi. Because my radius, when I'm doing my polar coordinates, is no longer rho. It's shrunk to become rho sine phi. And so it shouldn't be surprising. I should really view this as rho sine phi times rho. So one rho goes with the d phi, and rho sine phi goes with the d theta. That's the deeper way to look at what we're doing. Too much friction. So to do spherical integrals, and I go through and do in detail one of them in section 1, now that we have a range of integration, the hope is that we have a function that only depends on x squared plus y squared plus z squared. If it only depends on x squared plus y squared plus z squared, what can you replace x squared plus y squared plus z squared with in spherical? So what would x squared plus y squared plus z squared be in spherical? It would just be rho squared. So the example that was done in section 1 was a sphere of radius 2, and the density f of x, y, z was 4 minus x squared plus y squared plus z squared. If you want to figure out what is the density in spherical coordinates, you could start replacing z as rho cosine phi, x is going to be rho sine phi cosine theta, y is going to be rho sine phi sine theta, plug all of those in, or you could say, oh wait, I remember whenever I see x squared plus y squared plus z squared, that's just rho squared. So the integrand becomes just 4 minus rho squared. And then we would just integrate that, and it would just split as 3 integrals. So you would have the integral of 4 minus rho squared sine of phi d rho d theta d phi. Phi goes from 0 to pi. Theta goes from 0 to 2 pi. Rho goes from 0 to 2. And we can split this integrand into 3 integrals because it's a product of a function of rho times a function of theta times a function of phi. What's the function of theta here? It's just 1. The function of phi is just sine of phi, and the function of rho is 4 minus rho squared times rho squared. Okay. If you want to, you can still keep writing it down and doing everything slowly, or you can say, wait a minute, I've got theta goes from 0 to 2 pi, there's no theta dependence, it's just going to be 2 pi. And just save yourself a little bit of time. If you're comfortable doing that, by all means do that. If not, just also write down the integral over theta. Then I would have the integral phi goes from 0 to pi, sine of phi dphi, and in the integral, rho goes from 0 to 2, I will throw it, 4 rho squared minus rho to the 4 d rho. And now we have 2 self-one problems. And so this would then just become 2 pi, what has derivative sine minus cosine of phi, evaluated at 0 and pi. And then this would become 4/3 rho cubed minus rho to the 5th over 5 at 0 and 2. And so I'll just leave it as an exercise to finish the evaluation. Okay. So the last thing I wanted to just quickly do is show you how you can sometimes find integrals without knowing the antiderivative if there's a lot of symmetry. And typically we like to have antiderivatives, we'd like to be able to use the fundamental theme of calculus, but it's not always available. Or it's available only after some work. Let's say I want to integrate from 0 to pi halves of cosine squared of theta d theta. Well, if I want to evaluate this, I need to know what function has derivative cosine squared. I will assume that you don't remember that. I don't remember that, except for the fact that I just did this in section 1, so it's in my memory. But I do remember some trig identities. So the cosine of 2 theta is cosine squared theta minus sine squared theta, which is 2 cosine squared theta minus 1. So we get cosine squared of theta is 1/2 cosine 2 theta plus 1/2. So if I integrate, what function has derivative cosine 2 theta? Well, the derivative of sine is cosine. But if I take the derivative of sine of 2 theta, I'll get cosine 2 theta times the derivative of 2 theta by the chain rule. So I need an extra 1/2. So it would be 1/4 the sine of 2 theta plus theta over 2. And so you can check and see that that is going to have derivative cosine squared. And so I could evaluate this now by just evaluating these at pi halves and 0. So if I remember my trig, I can actually come up with the antiderivative for cosine squared. What I want to do is I want to show you a nicer way to do this integral. By symmetry, this integral is the same as the integral from 0 to pi of cosine squared of theta to theta. Because as I go from 0 to pi halves, so pi halves to pi, I'm just reflecting things, and because I'm squaring things, the minus sign doesn't matter. And so if I double this, I have to put in a factor of 1. Well, this is the same then as 1/4, the integral from 0 to 2 pi of cosine squared theta to theta. Because going up top is the same as going down below. But cosine and sine are the same function, they're just shifted by 90 degrees. So if I'm integrating cosine squared over a complete cycle of length 2 pi, that's the same as integrating sine squared over a complete cycle. So I can add sine squared and then divide by 2. This is the same as 1/8, the integral from 0 to 2 pi, cosine squared theta plus sine squared theta d theta. What's cosine squared plus sine squared? Cosine squared plus sine squared is 1. So this is just integrating 1 d theta. That's just 1/8 times 2 pi or pi over 4. So we can actually find some nice integrals without knowing the antiderivatives. And it's because we're integrating over a nice region with a lot of symmetry. But there was an antiderivative for this problem with a little bit of work to find it. So for extra credit, if f of x is the natural log of x, without using the web, without using Mathematica, find the antiderivative. What function has derivative natural log of x? We know the derivative of natural log of x is 1 over x, but going in the other direction is much higher. All right, this is a good place to stop for today.